Hello and welcome to another day of Advent of Code. We're back for day 16. And day 16 had a whole lot of reading. And also a lot of code. So we're not going to be coding this one live, but I'm going to walk you through my summary of the reading and then show you the code that I wrote and kind of the approach that I took. So the input of today's puzzle is a packet in hex form. And if we take a look at day 16 part 1, we look at one of the sample inputs, for instance this here, you'll see that it'll be in hexadecimal form, and the goal of part 1 is to parse the packet, and the packet rules are a little bit complicated. I'll step you through those in a second, as well as the associated code that I wrote for it. And the goal of part 1 is to parse all the packets and find the versions. The versions will be the first 3 bits of each packet, and some packets contain other packets, and part 1 is just sum up all those versions. Now, the way that I approached this is to first convert the hexadecimal string into a binary string, because we're going to be taking a series of bits and converting them into subparts, and this is kind of a crazy, insane packet format in that nothing is really fixed width. It's all kind of variable length packets and variable length chunks of bits that you pluck off. So converting it to a binary string made this way easier for me to think about it. And the way I did that was by taking each character of the string. This is maybe not the best. There's probably a better way to do this. I took each character of the string, parsed it in base 16, so that's what this int c16 is doing, and then converted it into a 0 padded 4 width binary thing. And so that's what this format string is doing here. So 0 pad, 4 width, and b is binary. And so I just built up my binary string in this way. There's many other ways to do this. This is just how I decided to do this. And then for each packet, you're going to plug off a certain number of bits. The first 3 bits are always going to be the version, and the next 3 are going to be the type. The way I did my parser is very similar to how I would write like a tokenizer for, I don't know, parsing some syntax or programming language or something like that. Basically a function which takes a position and returns a new position and whatever it parsed. In this case, I decided to represent this as a packet. You can kind of see the packet here. The packet has that version and type, and there are 2 types of packets. There's literal packets and there's container packets. And I just had them both specify the values there because it was kind of similar. You could kind of think of this as like a container union. Not quite that, but that's how I represented it. Okay, so once you've parsed the version and the type, you know whether it's either a literal packet or a container packet based on the type. And if the type is 4, you're reading as a literal packet. And the way literal packets work is they have 5-bit chunks. This is actually very similar to how UTF-8 works if you've worked with character encoding. So if you have, for instance, our snowman here, and you encode this as UTF-8, TF8, you'll see that we have 3 bits here, and if we do bin C for C in this, you'll see that they are each, wait, how did this one get bigger than 8 bits? What? Oh no, this is exactly 8 bits. Wait. Am I reading this wrong? Am I confused here? Yeah, because in UTF-8, the largest bit is set if it's a continuation bit. Wait, no, maybe it's the least significant bit. one way or another, UTF-8 communicates whether it has more bytes to read based on, I forget whether it's the first or last bit. I think it's I thought it was the first bit because that's how 7-bit ASCII works. But anyway, UTF-8 works very similarly to this encoding, so that's why this idea was familiar to me. But basically with this 5-bit chunk, the first bit is going to be whether there are more chunks, and then the last 4 bits are going to make up the number. So the way that I did this here, also I have this read function which made this much easier for me. I input the starting index and output the ending index. So whatever it parsed, the next thing can call this function again and continue parsing. And I had this read function which takes in a number of bits. It uses this non-local feature, which allows this function to modify variables in a scope above it, and basically parses the chunk of binary string and increments that number. And so that made reading chunks much more convenient. But when we look at our literal chunk here, we start first by reading that 5-bit chunk. We add our number based on this little chunk here, and maybe this is actually easier to read as this, because 0 plus equals is kind of nonsense. And then we check the 5th bit, or the furthest leftmost bit, as to whether we're continuing. So that's kind of what this continuation loop is doing here. And then we shift and read. This is basically my literal reading part. And you'll note that I make a packet here, but I only specify n. I don't specify these sub packets that we had up here. And this is kind of, one type has n, the other type has sub packets. Okay, and if we're not a literal packet, we are a container packet. There are actually 2 types of container packets. If I was designing this protocol, I probably would not have had 2 different types here. This is probably just added to make the problem slightly more complicated, but that's fine. So you need to grab the mode bit here, and for mode 0, there is going to be a 15-bit number which says how many bits represent the subpackets. It doesn't tell you how many subpackets, so you basically just have to continue to read until you've exhausted all of those bits. And here I am recursing. I'm basically abusing my parser to do recursion and updating j, j being the position where it started at, and then this is the position that it ended at. And so it's just updating that in place, kind of. And I collect all the packets that I parse, and then this form of the packet doesn't have an n, but it does have a subpackets tuple here, and I just return that out. The other mode 1, has 11 bits, and that's the number of subpackets. This is probably how I would have designed the protocol, both because it's shorter to transmit and easier to parse, because you don't have to guess at what how much more there is to read. Like, it's very explicit about how much to read. But yeah, for this one, we read the number of subpackets and then basically read that number of packets and return that back. And so once all of this parsing is done, this big, long, recursive parse packet function, we have just one packet out here. And for part 1, we're supposed to sum up all of the values in version. And the way that I did that is basically just have a stack and recurse through the stack and sum up all the versions. So while there's something to do, we have a total here. We grab the last item off of our stack, we add up its version, and then we add on whatever subpackets it has. For the literal packet, this will be empty, and so it'll stop. But for the non-literal packet, this will pick up all the children. That's part 1. Part 1 doesn't really do anything with these packets. It mostly is just like a nice little checksum. And this was one of the inputs that they gave. There were a bunch of sample inputs. I really only tested one because I was trying to go fast. But that's part 1. For part 2, that type field that we were kind of ignoring, except for literal packets, now has a meaning. It either is some sort of math operation or a logical operation. If we take a look at part 2, I still used exactly the same parsing that I did for part 1, so we'll ignore that. But then I had another recursive function for taking the packet and converting it into a value. So basically, parse the packet and then convert it into a value. And for each of these, there's a different operation. So for 0, it's just sum, and there's a built-in sum in Python. For multiply, it says multiply all the subpackets together, and the identity for multiplication is 1. So that's why I started my value with 1 and then multiplied these all up here. I could have used reduce, but I actually think this is a little bit more readable. Min and max are simple in Python. And again, note that I'm recursing here. So for each subpacket, I'm calling val, hoping that the recursive stuff is going to resolve that to a particular value for us. So we don't have to really think about the children. It'll just handle it through recursion. And this is kind of our base case here for our literal packets. So we just return back n. There's no recursion for type ID of 4. 5, 6, and 7 are comparison operators. The spec does say that there will be exactly 2 subpackets for each of these, so I didn't bother with any bounds checking, but if you're being a little bit more careful, you might assert that those have the right length. And I just left this in case I made some sort of programming mistake. But yeah, that's basically how I approached day 16. Hopefully this was helpful, and I'll see you around for the next day.